In this lesson, we're going to look at Chapter 3, Section 5. We're going to be looking at rational functions. Our main objective is to graph rational functions. And so to do that, we're going to need to know some information about the rational functions. Things such as what's the domain, what's the range, does the rational function have any vertical or horizontal asymptotes? We'll also be looking at x and y intercepts to assist us in graphing these rational functions. So what is a rational function? We've had limited exposure. Now we're going to get more. But a rational function is of the form f of x equals p of x over q of x, where both p and q are polynomial functions and q of x cannot be 0. So the parent function for a rational function, the one that's the simplest form of a rational function, is f of x equals 1 over x. So that's also called the reciprocal function. So just think fraction when you hear rational function. So over here on this grid, we're actually going to plot some points and we're going to graph f of x equals 1 over x to see what it looks like. Okay, so on the right-hand side, I have a table of values here. Okay, right here where this dashed horizontal line is, okay, we can think of 0 being in here. Okay, so just think about that for a second. If I were to plug in 0 for x in this function, I would get 1 over 0. 1 over 0 is what we call does not exist or undefined. Something interesting on the graph is occurring at x equals 0. All right, so for our function right here, let's go ahead and replace in -2 for x. The output or the y is -1/2. I'm also going to squeeze in a -1 that didn't make print for some reason here. So plug in -1, 1 over -1 is -1. Now go to your calculator. What's 1 divided by -1/2? The result would be -2. Then we're going to choose some other x values on the other side of x equals 0. So let's plug in 1/2 for x. So 1 divided by 1/2 is 2 on the calculator. Plug in +1, the result is 1. Plug in +2, and the result is half. So let's take these ordered pairs and plot them on this grid to kind of see if we can kind of see what the graph looks like. So let's plot -2 and then -1/2. So that'd be about right here. Let's plot -1, -1. It'd be about right here. Let's plot -1/2 down to -2 about right here. If I were to continue adding x values in this t-chart beyond what I have here, the trend of these points right here suggests that my graph may just continue downward like this, closer to the negative y-axis, and I'm going to put an arrow down here. The graph also, the points that I have also suggest that if I were to continue back to x values that get smaller, that my graph is actually going to continue and just hover really close but underneath the negative x-axis. So we want to extend and draw an arrow. All right, let's plot these points right here. Let's plot 1/2, which is right here, to 2. Let's plot +1, which is here. And let's plot the point 2, 1/2, which is here. These 3 points, again, when I start to connect them, suggest that if I were to add some more points here under the x column, or at least x values, that my graph would continue outward this way. Also, the trend here suggests that if I were to plot even smaller positive x values, that my graph would extend up here, closer to the positive y-axis, heading off towards infinity. Okay, notice that we have a break in this graph at x equals 0, that if I tried to draw this graph, I would have to lift my pencil at x equals 0 to get to this other branch of this rational function. So x equals 0 is what we call a vertical asymptote. It's a vertical asymptote. And it's actually the restricted value of the function. And a while ago in section 2.6, we saw restricted values come from setting the denominator of the equation, if we have a rational function, equal to 0. All right, so let's come back over here. Again, this is the most simple rational function. It's called the reciprocal function. The domain is all real numbers except for 0. So if you swing your pencil across this way from negative x values to positive x values, the only place where I don't have an x value on a point of the graph is at x equals 0. So that's our restricted x value, which becomes our vertical asymptote. The range is negative infinity up to, and notice when you get to 0, y equals 0, you'll never be able to connect with the graph, either to the far left or the far right. But once we leave y equals 0, then all other y values are present on the graph. So the domain and the range are the same in this case. So rational functions have asymptotes. We've already kind of talked about a vertical asymptote. An asymptote is a line that the graph approaches. It might touch, and graphs can have vertical, like this, asymptotes. They can have horizontal asymptotes. They can even have slant asymptotes. So in our study in this course, we won't be looking at slant asymptotes. We'll just be looking at vertical and horizontal asymptotes. Right, we did graph 3 points on either side of this vertical asymptote at x equals 0 to get an understanding of what this graph would look like. Vertical asymptotes, a vertical line, x equals a, the graph approaches but will never touch a vertical asymptote. And the restricted values of the domain determine this vertical asymptote. A rational function can have more than one vertical asymptote, and we'll see that shortly. So again, f of x equals 1 over x. The restricted value in the domain is 0, because when you let x not equal to 0, we understand that x couldn't be 0. Dividing by 0 is not a good thing in math, so that's what we look for is restrictions, and that comes from the denominator of this rational function. So the restricted value is 0, therefore the vertical asymptote has the equation x equals 0. Any vertical line has an equation that starts x equals. Okay. All right, so what's important to us is to think about the domain, and if we have any vertical asymptotes, and also if we have any what we call holes in a graph. And so that's what we're going to explore next. And we have to have an understanding of those things so that it'll help us and assist us when we get to our main objective of graphing rational functions. So at this point, before I continue on this paper, I want to kind of connect back to something we did in the past. So actually what I'm going to put here is the key that I have from way back in chapter 2, section 6. Down here at the bottom, well, what we were doing on this page is we were finding domain restrictions of rational functions and also even root functions. Today, we're just looking at restrictions on rational functions because that's our objective for today. So I want to come down here. What we did in the past is we determined the domain. Polynomial functions have a domain of all real numbers, so we're not interested in polynomial functions. We're not interested in even root functions because our focus is on rational functions. So let's start by looking at what we did in the past with this equation. We were asked to determine the domain. So what we did for this rational function is we took the whole denominator and we set it not equal to 0. Then we added a 2 to both sides and divided by 3. And we got that x cannot be 2/3. X can be any other value but 2/3. So what is the domain? Well, the domain is from negative infinity to positive infinity with the exclusion of x equals 2/3. So now today we know that this restricted x value is going to be a vertical asymptote. It may be a hole, but we'll talk about that later. Okay, way back here, we did not look at the graph of this function. We were just interested in finding the domain. So this is the process we went through. But I think now that we're looking at graphs in this section, okay, I want to bring in a graph of this rational function. So I've got this handout. And so right here, these are the graphs from section 2.6, and this is the one we were just talking about. So the graph of this rational function, okay, starts over here at negative infinity, right below the negative x-axis. And if I draw it, I can continue, and then it continues downward here. I'd have to lift my pencil at this x value of 2/3. Then I'd have to jump back on the graph up here and continue drawing it out this way to positive infinity. So we can see that from our previous work, we knew that x could not be 2/3. So if I look over here on this graph, I can see if I kind of dash in a vertical line here, okay, that my graph has a vertical asymptote at x equals 2/3. So we named the equation of the vertical asymptote x equals 2/3, but 2/3 is not part of our domain. Okay, back in this section in 2.6, when we were still trying to determine domain, let's look at another rational function that we found the domain of. So this is an even root function. We don't want to look at that because our study today is about rational functions. So we're going to look at these two examples, and they're graphs that we didn't look at before. Right, back here in this lesson, we were interested in the domain. So what we did, we knew it was a rational function. We set the denominator not equal to 0. We subtract a 4 from both sides. So we got x squared does not equal -4. Well, the next algebraic move on here would have been to bring in the square root. So if we bring in the square root on both sides of this equation, we're going to end up producing an imaginary number. So we said, okay, well, there's no restricted x values that are real, so we have no restriction. The domain would be all real numbers. We didn't look at a graph then, but let's take this same equation, and now, right here, I produced a graph. This graph represents this equation. Notice that we have no restrictions, no x restrictions. The domain is all real numbers. So that means, can I start here on the graph and draw this graph? It has a little dip in it, cuts through the origin, kind of spikes up, comes down, but yet hovers closer to the positive y-axis. Can I draw this graph without ever lifting my pencil? Absolutely. And that would represent a domain of all real numbers. So I have no vertical asymptotes. So the domain was all real numbers. Back over here, the domain went from -infinity up to +2/3. We can't include 2/3, so then we continue to +infinity. All right, we had one more rational function way back here in 2.6, and it was this rational function. So what we did is we set the denominator not equal to 0, and then we had to factor. So we used our factor sum chart, and we ended up with this binomial times this binomial does not equal 0. Set each binomial, that means two terms, equal to 0. The factor of x plus 4 gives us a restriction of -4. And this factor, when set not equal to 0, gives us a restricted x value of -2. So if I kind of organize these two numbers on a number line and put -4 to the left because it's smaller than -2, okay, and I have to exclude those, okay, then I knew from there that my domain would be -infinity up to the smaller restriction, and then again from that value to the next restriction, and then from that last restriction of x equals -2 to infinity. So let's see what the graph looks like here for number 6. Okay, we almost should think that we're going to have two vertical asymptotes at x equals 2 or -2 and x equals -4. So let's look at the graph of this equation. So here it is right here. Well, notice when we start to draw the graph from far left and I kind of start to swing downward, okay, and then to lift my pencil, I'd have to get back up here. Right in between these two branches of the graph, if I dashed in a vertical line, if you count the tick marks, that's actually x equals -4. And we knew from our previous work that x could not be -4, nor could it be -2. One would think when you started to graph at x equals -2, which is right here, one would think that the graph would behave like it had a vertical asymptote, where the graph is drawn to that, but that's not what's happening here. I have a vertical asymptote at x equals -4, but what's going on at x equals -2? Well, we'll have to see that when you factor this denominator and you get x plus 4 and x plus 2, notice that x plus 2 is a common factor with x plus 2 in the numerator. When you have common factors like this, the restricted x value that comes from this common factor actually won't be a vertical asymptote. It's going to be what we call a hole in the graph. So my software, when I generated this, does not show that there's a point that's removed right here at x equals -2. So we have to go back and adjust and act like there's no part of the graph there, because there's not. There's really a gap there. It's just that some software programs just don't show that. It's real difficult for them to do so. So I still have two restricted x values. It's just that at x equals -4, I have a vertical asymptote. And notice that we do not have an x plus 4 in the numerator to cancel with this x plus 4, and that's why we do have a vertical asymptote. Common factors that cancel, okay, at their zeros, so x equals -2, produce what we call a hole. Now, if I wanted to find the y-coordinate of that hole, I know the x-coordinate of that hole is 2. If I wanted to find the y-coordinate of that hole, I would actually have to go in and simplify, cancel out the common factor, and I have a 1 in the numerator. Now I can plug in 2 for the x here in the simplified rational function. I'd get 1 over 2 plus 4, which is 6. So the y-coordinate is 1/6. Again, I plugged in 2 to the simplified rational function, which was 1 over x plus 4. All of this is going to help us, all these ideas are going to help us when we go to our main objective today, which is to graph a rational function. All right, so let's return to our notes and do some practice with that, with all that we've just done. So here we want to find the domain and any vertical asymptotes. And these are the steps that we're going to take to do so. We're going to factor the expressions first if possible, both the top and bottom. We're going to set factors of the denominator equal to 0. We're going to actually set the denominator factors to not equal 0 to find the restrictions. If a factor cancels, it still gives a restricted value in the domain, but it's not a vertical asymptote. It's just a single missing value in the graph called a hole. The location of the y value of the hole can be determined by replacing that x value of the hole into the simplified rational function. That's actually what I just talked us through right here. So, but at least it's printed, and if you forget, which, you know, that's common, then you can go back and read through and go, oh yeah, that's how I have to identify a hole and find the y-coordinate if I'm supposed to of that hole. All right, so down here we have some examples. We have A, B, C, D, E, and F, and I think we have some more on the other side too. Let's practice finding the domain, vertical asymptotes, and any holes that we might have on each of these functions. All right, so we've seen f of x equals 1 over x. We actually graphed it up here. How do we find the domain when we're asked to do that? Well, I'm going to go ahead and set the denominator, which is just x, not equal to 0. So the domain is actually all x values except for 0. And we report it this way using integral notation. All right, now we have to consider, do we have vertical asymptotes or holes? Well, I need to factor, but I can't really factor. Do I have any common factors? No, I have x down here, but not an x up here. So that tells me that this restricted value is now the equation of my vertical asymptote. So we put the vertical asymptote is always x equals, and it's the restricted x value. Holes, no, we have none because we don't have any common factors. So just verify with what we have up here. Is the domain of this rational function all real numbers except 0? Yep. Do we have a vertical asymptote at x equals 0 where the graph never touches? Yep, we do. Do we have any holes? Nope, we don't. Okay, let's look at B. Let's find the domain. All right, well, that's by setting the denominator equal to 0. Okay, so we're going to actually set it not equal to 0. Let's go ahead and factor. This is a difference of 2 squares. So this will factor into x and x here, and one's a plus 5 and one's a minus 5. We'll set each factor not equal to 0. So x plus 5, that factor gives a restricted x value of x cannot be -5. And then when you set this factor not equal to 0 and add a 5 to the other side, both sides, you'll get x does not equal +5. So that tells me that these two x values cannot be part of all real numbers. So let's start at -infinity. The smaller of the two numbers on a number line I'll run into first, which is -5. I have to start again at exactly -5, continue along until I get to any more restricted x values, which is 5. And then again on the other side of 5, go until you get to infinity. So on these bookends here, we should have -infinity and +infinity for these rational expression domains. Do we have any vertical asymptotes, or we have holes? Do we have one of each? Are they both vertical asymptotes at those restricted x values, or are they both holes? It could be any kind of combination. Well, for us to figure out if these two restricted values are vertical asymptotes or holes, we want to see if we have a common factor with the numerator. So let me kind of clean this up. So the numerator is just x. So I do not have an x minus 5 in the numerator, so x equals 5, that restricted x value that comes from this factor, x equals 5 is a vertical asymptote. Does x plus 5 have a common factor on top? Nope. There's not another parenthesis of x plus 5. So the restricted value from this factor, which is negative 5, it becomes a vertical asymptote. So now that I've considered all restricted x values and there's none left, then that means we have no holes. Let's go to a graph. So this is our b equation. Here's the function, okay, and this is the actual graph that's produced. So based on what I see here in the graph, I know the graph is kind of hovering near the negative x-axis. We have to turn downward, which suggests a vertical asymptote. Lift your pencil so we can continue drawing the graph. We'll dash in right here at x equals negative 5, a vertical asymptote. Continuing drawing, and then right here, the graph suggests that I continue downward. I have to lift my pencil at x equals 5 so that I can continue drawing the rest of this graph, this branch. So dash in another vertical line, and we call that the other restricted x value, x equals 5. That's the equation of the vertical asymptote. So our objective is to draw these types of graphs, but we have to know where is the location of the vertical asymptotes to assist us. So let's go back to C. All right, I see that on C, if I factor the denominator, I'm going to get the same as what I had previous. So the denominator factors as such. To find the domain first, I'm going to set the denominator not equal to 0. Doing the same work I did over here, I'm going to get x cannot be 5 and x cannot be negative 5. So now for this problem, our domain is the same thing as in example B. Okay, so now do we have two vertical asymptotes for this graph at x equals 5 and negative 5? Well, that requires that we look to see if we have any common factors. Well, notice that x minus 5 can be grouped together in the numerator, and it actually divides out with a common factor in the denominator. So the 0 of this factor, the restriction, was positive 5. That actually is going to be our hole. So the hole is going to occur at x equals 5. So let's look back. X plus 5 doesn't cancel with anything in the numerator. So the restricted x value, x equals negative 5, is actually our vertical asymptote. So for this graph, when we look at it in a minute, we'll have a vertical asymptote at x equals negative 5, but we're going to have a hole at x equals 5 that we're probably going to have to remove just because of my software. So let's look at C's graph. So C's graph is here. So we have the graph coming on the screen just right below the negative x-axis. We dip downward, that suggests a vertical asymptote. When you lift your pencil to continue drawing, dash in at x equals negative 5, a vertical line. That's the equation, x equals negative 5 of that vertical asymptote. Well, remember the other restricted x value is x equals 5. So we continue, and it looks like we never have to lift our pencil again. But at 1, 2, 3, 4, 5 right here, the software program can't remove that point, discontinuity, that hole, but there really is one there. Well, if we want to know what the y-coordinate of that hole is, remember, what we do is we take 5 and we plug it back into the simplified equation. Well, the simplified equation is 1 over x plus 5. So plug in 5 for this x and we get 1 over 10. So if we wanted to know the y value of the hole, we would plug in the x to the simplified equation. So we still have two restricted x values where we have to lift our pencil. One's a vertical asymptote and one's a hole. No, it's a lot. Let's go ahead. We need a few more examples. So let's look at D. Okay, so I'm going to go ahead and try and factor everything first. So equals 5x stays the same. I notice that I can pull out an x from the denominator's two terms. That would leave x minus 4. Let's go ahead and tackle the domain question. So x times x minus 4 cannot equal 0. So that means x cannot be 0, and x minus 4 cannot be 0. So add a 4 to both sides, x cannot be 4. So from the factor x minus 4, the restricted x value is positive 4. So let's report the domain. So we're going to come from negative infinity. The first restriction we're going to hit is 0 because that comes before 4. So then start again on the other side of 0, continuing until you get to the second restricted x value, and then continue from 4 on to infinity. Okay, so are these restricted x values vertical asymptotes or holes? Well, let's look at the factored version of our problem. All right, it's maybe not obvious, but this x and this x are common factors and they can divide out. The restricted x value that came from those common factors is 0. That's going to be your hole. The hole is at x equals 0. Notice that x minus 4 does not have a common factor with another x minus 4 in the numerator, so that restricted x value, x equals 4, would be your vertical asymptote. So we have a vertical asymptote at x equals 4, but a hole at x equals 0. So I've got the graph here. This is D. I'm coming on close to the negative x-axis. I continue downward. Okay, I see that the graph goes down. On the other side, okay, of this x equals 4 right here, I'm going to dash in a vertical asymptote. The graph is still coming down. This is x equals 4. And then it continues off this way. And it stays above the positive x-axis. It just gets close to it. That's our horizontal asymptote when we talk about the extreme ends. Okay, but remember we had that restricted x value of 0. I'm supposed to lift my pencil at x equals 0. So when I kind of look back at graph D, I look to x equals 0 and I look down because that's where the graph is, and I actually take out that point right there at x equals 0. So what's the y-coordinate of this hole? We'll take your 0, which is the x-coordinate, come back to the simplified rational function where we canceled off the common factors, plug in 0 for x, we're going to get 5 over negative 4. So the y-coordinate is negative 5/4, which kind of makes sense because that's a negative number, and it definitely looks like it's negative right here. Okay, let's go to E. All right, can I factor the denominator? No. This is not a difference of two squares, it's a sum of two squares, and it will not factor. So let's just take the denominator the way we see it, find the domain. I can't factor it. Let's subtract a 36. X squared equals negative 36. Kind of predict ahead. If you were to take the square root and put a square root over a negative number, you're going to get an imaginary solution. So there's no restrictions. So if I have no restrictions, that means my domain is all real numbers. If I have no restrictions, then I have no vertical asymptotes, and there's no way I can have any holes. None and none. So let's go to the graph of E, problem E, which is right here. Notice the graph is hovering close to the negative x-axis, and it kind of bumps up, but there's never a place where I have to lift my pencil. So this graph accurately reflects the domain of all real numbers. Let's look at F. F's denominator is already factored. That's great. There's nothing more I can do with the numerator. Let's go ahead and find the domain. Let's set each factor not equal to 0. So the restricted x value here is 5. If I subtract a 4 to the other side, the restricted x value here is negative 4. So the domain, I come up from negative to negative infinity. I'm going to hit this first restricted x value at negative 4. Start again at negative 4. The next restricted value is 5. and then start again at 5 and conclude at infinity. So you've got your infinity bookends here, negative and positive. All right, so let's go back and look at each of these restrictions. Well, when I look at x cannot be 5, it comes from the factor x minus 5, but there's not an x minus 5 in the numerator to cancel with it, so that becomes a vertical asymptote at x equals 5. Likewise, this other factor of x plus 4 does not have a common factor with the numerator, so we also have a vertical asymptote at negative 4, which means I've considered all restrictions. None of them have a common factor, so there's no holes. There's actually just 2 vertical asymptotes. So let's verify that through the graph. So the graph of f has 2 vertical asymptotes. So the graph is actually kind of hovering right here, not close to the x-axis. It has a different, what we call horizontal asymptote, where it kind of bottoms out, but it doesn't get close to the x-axis. It gets closer to a different y value. And that's the next thing we're going to cover is horizontal asymptotes. But just for right now, we're going to draw this graph, this branch. It continues upward. I'd have to lift my pencil to come down here and continue drawing. So right here, we have a vertical asymptote. So that vertical asymptote occurs at x equals negative 4. So then we continue drawing this graph, and we come around, swing around, and it continues downward here. I'd have to lift my pencil to get up here to the other part of the graph so I can continue drawing it outward this way. Well, right here is where we have our second vertical asymptote, and if you count the tick marks, that's at x equals positive 5. Okay, so a couple more. So let's turn the page. Hopefully you're kind of getting the feel for the domain vertical asymptotes and holes. Okay, let's look at G. The numerator is already factored. Let's go ahead and factor the denominator. And I'm just going to kind of quickly factor it, saying that use a factor sum chart for that quadratic. You get x plus 3 and x plus 2. So let's find the domain. Each factor gets set not equal to 0. So we'll subtract a 3. We have a restricted x value of negative 3, and we have a restricted x value over here from this factor of negative 2. Domain, negative infinity, negative 3 is smaller, it comes first, etc. Okay, do we have vertical asymptotes or holes? Well, when I look at x cannot be negative 3, it comes from this factor, but notice the numerator, if I kind of group it, that's the same factor as down here. So x equals negative 3 is the x coordinate of the hole. X plus 2 does not have a common factor with the numerator, so the restricted x value of negative 2 would be your vertical asymptote. Okay, so let's look at the graph. So we should have a vertical asymptote at x equals negative 2 and a hole at x equals negative 3. So negative 2 is here, so that's our vertical asymptote. The equation is x equals negative 2. Now let's find negative 3, which is right here. Find the graph. Here's where our hole is supposed to be, right here. What's the y coordinate? Well, we know the x coordinate is negative 3. So let's go back to the simplified equation where I canceled out the common factor. Remember, there's a 1 up here still. Let's plug in negative 3 for x, the x coordinate, and when we do that, the answer is negative 1. And that makes sense. Looks like that y coordinate is down here at negative 1. All right, 2 more. Let's look at h. I cannot factor this denominator because it's not a difference of 2 squares. I have to simply just set the denominator not equal to 0 to find the domain. Subtract a 25. Again, if you were to bring in the square root, you would have an imaginary solution, so that means there's no restrictions. No restricted x values. Your domain is all real numbers, so we can't have any vertical asymptotes or holes. So real quickly, looking at h's graph, it should be continuous to where we never have to lift our pencil, and that's indeed what's happening here. Okay, the last one suggests that we have a vertical asymptote maybe at this x value, 4. I'm just kind of predicting here. There might be a hole somewhere, I just can't see it, but the equation will help me determine that if I have a common factor. All right, for I can factor the denominator. I can pull an x out from both these terms. Okay, so notice that we're going to set the denominator's factors not equal to 0. So we have two restricted x values, 0 and 4. That'll help us compose our domain. All right, vertical asymptotes, okay, in holes. Well, I do see that x and x are the same common factor, so the restricted value that came from it is 0, so that's going to be our hole. X minus 4 does not have a common factor with the numerator, so that must be our vertical asymptote. Remember, we saw a vertical asymptote at x equals 4. But now we know we have a hole at x equals 0. So go to where x is 0, look down, that's where the graph is. And that's where we're going to take the hole, put the hole in there, or take that point out. So what's the ordered pair that names that hole? Well, it's x equals 0. Let's plug 0 into the simplified fraction. So 1 over 0 minus 4 is negative 4. So 1 over negative 4, or simply negative 1/4. Well, that's a lot of background, but I just want us to really understand when we're finding things graphically, what does that look like? So that when we do try and accomplish our main objective in this section, which is to graph a rational function, we have a pretty deep understanding of why that graph looks the way it does. All right, we'll continue in the next lesson by looking at horizontal asymptotes, and then we'll finally get to graphing.